Hello and welcome to a presentation for OpenPOWER from the Libre-SOC project. With many thanks to OpenPOWER Foundation and Linux Foundation, and also to NLnet for sponsorship of this project. Why are we doing another system on a chip when there's plenty available in the market already? Well, a simple answer to that one is that we've got things like Spectre and Meltdown. We have Intel Management Engine, which provides us with backdoor kind of spine code processors. These are also in AMD, also has a similar issue. There's QA issues in Intel's development, which were recently highlighted by Apple. And just want opportunities to do better. Another reason is that there are, in system on a chip world, which is a fully integrated processor, there are endless proprietary drivers, which ends up affecting the product development cost. You license a hard macro for 3D, and it comes with a proprietary software driver, and you don't have any choice about that. Consequently, when fabless semiconductors pick design a particular chip to save on their development costs, they go for the easiest solution, and unfortunately absolutely everybody has done that. There are no entirely Libre system on a chip for which the full software stack is available. Consequently, that's a product opportunity for us. There's also an opportunity to drastically simplify driver development and engage in long-tail markets. Now, the typical way that the GPU is developed is that you have your user space code, which then calls into a kernel driver. The kernel driver then passes over a memory map system, uses shared memory, PCI Express bus in the case of an external GPU, and then unpacks the function call arguments for the OpenGL call, whatever it is, makes the functional call on the GPU in a foreign architecture, and then passes the results all the way back to the user space application, the 3D application. We decided to take a different approach, where to actually do a hybrid architecture, which put it into the actual the instruction set, and it gets executed by the power instruction set. The other reason this is good enough for Zenny is because for 30 years I always wanted to design CPU. Why we've chosen OpenPOWER? Well, to answer that, first we have to go over some evaluation criteria. A good ecosystem is absolutely essential. We need Linux kernel, UBoot compilers, OS support, bin utils, everything, and we need reference implementations, because otherwise, if we don't have them available, we're going to have to spend the time and effort creating them, and then convincing people, customers, that they should adopt it, and that is an extraordinarily hard sell when we don't need the hassle. So we're not going to do that. It needs an extremely supportive foundation and members, and we need to be able to submit ISA augmentations, which should be properly peer-reviewed before being allowed to become part of the ISA. The other thing that's critical for us under the NLNet's Privacy Enhanced Trust Program, and as a business justification for full transparency and trustability, no NDAs are signed, and we need this full transparency. We can't even engage in the working groups without there being full auditability by our customers. So with those criteria in mind, we then looked at a very comprehensive review of all the available instruction sets. RISC-V turned out to be total opposite of what is advertised as it's closed secretive mailing lists, closed working groups. We tried really hard to earn very reasonable requests to be included, and there was absolutely no exceptions or response to our transparency requirements. Plus, they're just not established enough. At the time we looked, the MIPS Open Initiative website was offline. Bless them. I would really like to have considered that more value soon, but you know, if they haven't got a website up and running, I just can't use it. Can't consider it. ARM and x86 proprietary, x86 is far too complicated. OpenRISC 1200, although extremely good, there's just not enough adoption compared to ARM, OpenPOWER, and RISC-V. Now I use this as a GPU. Meow is not actually a GPU. It's a AMD compatible vector engine. Rolling our own instruction set was just out of the question for a hybrid architecture, because you actually have to do the full standard instruction set as well as just and then add the GPU stuff on top of it. OpenPOWER has been established for decades, has an excellent foundation. We've got microwatts as a reference platform, and with many thanks to Hugh for introducing us to people. We've found that they've been extraordinarily approachable and friendly and supportive of the strategy that we've come up with. So, what goes into a typical system on chip? I have to explain this because many people think of processor and they think automatically Intel, Northbridge, Southbridge chip. The peripherals are totally separate. It's completely different. Everything is not necessarily on the same die, because you sometimes get multi-chip modules, but you basically have a built-in GPU, a built-in VPU where it's a shared memory bus. It's third-party license, so for example, Vivant, which is, I think it's been bought by Synopsys, is $250,000 licensing cost for GC800, for low power embedded things, and most fabless semiconductors I mentioned earlier would just go for that. It's just simpler, but it's simpler to to get your building blocks and put it together. But it means that both the GPU and the VPU, unless they've been reverse engineered, which is itself an extraordinarily high cost time of development, and then you end up with the older version of whatever it is that you're doing, running your software on. You're always playing catch up with reverse engineering, and it's a minimum 3-year delay from the time that the product would actually started. It's just commercially not viable. So you end up with this proprietary software for the video decode and proprietary software for the GPU, which impacts you've got these opaque blobs and you can't do software development on them. You get you single step into the thing and it's been stripped of all the debug symbols. So you can't work out if there's a bug in your software or there's a bug in the driver, which really does happen. Samsung's had that. Power VR has just been hugely unstable and an absolute nuisance, and so on. Excuse me. You also get these fully integrated peripherals, so everything is on a chip, and your target price for your chip is typically between $2.50 and $30, depending on the market. So overall, it's radically different from your average Intel processor or AMD processor, and certainly different from the IBM Power 9 core, which is over 200 watt and focused on high performance I/O. So this is just a quick illustration of the idea. So those two blocks, the video processing and the 3D instructions, are inside here as actual extensions to the OpenPOWER instruction set. And we'll be doing an out-of-order design and adding simple view vectorization. More on that in a bit. So here's your peripherals, and you typically have a PinMux, which maps all of these 1,000 pins down to only 200 or however many it is. This is just a typical chip, 2.5 to 5 watts. So it's it can be a ceramic package or a plastic package, no heatsink needed, and it's extremely compact, and you can typically get away with if you use miniature components, you can get away with about a 30 by 40 millimeter PCB for the entire design, including power management, the processor, and NAND flash and memory, which will be 3D stacked. So where we're starting, the first thing was get a basic core working on simulation and then on an FPGA. We're using microwatt as a reference to do that, and we've successfully managed to do that a couple of weeks ago on a Versa ECP5, which is a fully free software toolchain. Next, we're going to do a low-cost test chip in 180 nanometer. This will allow us to iterate on and gain confidence in our ability to develop a chip without wasting vast sums of money on 20 nanometer or whatever it is, multi-vendor program costs. If we do this the basic in 180 nanometer, it's only about 18,000 US a time, which is we can do a hell of a lot of iterations on that before we move and get the core right first before we move on to faster designs. So in parallel to that, under the watchful eye of the OpenPOWER Foundation, we'll be developing a vector instruction set with 3D and video extensions. We're going to implement a vector instruction set of Simple V in a simulator that will allow development of bin utils and the 3D GPU compiler, the shader engine. Then we'll implement in HDL, run that under simulation thing, and then put it into FPGA, and finally, only when it's been ratified by the OpenPOWER Foundation, we've got permission to do so, we'll put it into silicon. Then we sold some lit chips, make a lot of money, and repeat the process again. So what's different about LibreSOC? It's what's called a hybrid integrated CPU. So the CPU is the GPU is the CPU, and likewise for the video processing. There is no separate VPU, GPU, pipeline, or core, or instruction set. So apologies for emphasizing that, but it takes quite a long time. We've found from experience it takes quite a long time for that to sink in. We are actually adding 3D and video instructions to power instruction set, not creating a separate GPU with its own utterly separate pipelines into cache, etc. It's literally inside the Power SA core, the main core. Right. So it's also written in nmigen, which is a Python-based HDL, not VHDL, not Verilog, and definitely not Chisel 3 with Scalar. We spent several months evaluating different HDLs, and this is an extremely important, extremely easy decision for us to make. The other thing that's different is Simple V vector extension. If you look up simply considered harmful, which is on sigarch.org, we based the Simple V on the Cray vector loop system, which effectively, but went a step further, and effectively it's like MMX instructions. It's a hardware for loop on the standard scalar instruction set, where it increments the program counter, pauses the program counter, and increments the register numbers on the scalar register numbers from 0 to VL-1, effectively. So it's conceptually similar to zero overhead loops from DSPs. We're doing a hybrid architecture, we're calling it Augmented 6600. So the CDC 6600 is a design from 1965, but the augmentations are not. And Mitch Alsop very kindly helped us, spent several months explaining this to me on comp.arch, how to add precise exceptions, multi-issue, and much more. I won't go into a lot of detail, but basically the academic literature on 6600 is utterly misleading, simply because Seymour Cray and James Thornton back in 1963, when they designed the 6600, solved problems that they didn't realize existed. They were literally the first people to do an out-of-order superscalar architecture, and did didn't realise that things were difficult. Consequently, they didn't put it into the literature or the pattern, which is, yeah, you get the idea. So we're doing a front-end vector instruction set, this simple V, but it's at the back end it will be a predicated or masked SIMD pipelines, and nmigen, which is Python object oriented, was strategically critically important for us to achieve this in a reasonable amount of code, maintainable code. We're doing out of order instruction set, which when combined with simple V, that for loop, hardware for loop, issues scalar operations, but it issues them all in the same cycle, and consequently they can be turned into SIMD at the back end without the developer needing to know that it's SIMD, and that has a huge saving for the compiler writer on the complexity of things. You see that SIMD considered harmful, and it saves clock cycles, everything is a huge benefits to it. Then what we'll do is we'll add IEEE 754 sine, cosine, atan, log 1p, etc., normalize and things as scalar operations to the power instruction set, and simple V will vectorize those automatically and inherently. Why we chosen nmigen? So first thing we do is evaluate other HDLs, and we get a sort of an idea of the criteria that we need. The first thing to appreciate is that our team is primarily software engineers, not hardware engineers. So Verilog was designed in the 1980s for doing unit tests, when people were still heavily doing gate level design. VHDL again is a procedural language similar to BASIC and Fortran. It does, however, have records, which is really nice. Chisel Scalar is is object oriented, but it's extremely obscure language, suitable really only for research. It's just not. You can't intuitively. You can't just obviously read the code and understand it. I've tried. PyRTL is a Python-based HDL thing, but the community is not large enough behind it. And myHDL is a subset of Python only, so it's basically Verilog in a Python syntax, and consequently only the subset of Python which maps to Verilog is supported. So from this you can see we're slowly forming a set of criteria, which basically Python is the only language which fits, and we then decided to apply those same criteria to the HDL itself, although that HDL is a much smaller community. And it turned out that nmigen was the only one that actually meet those similar criteria. So it uses Python to build an abstract syntax tree in memory, which is then handed over to Yosis to generate an ilang file, and then you can use the write _ Verilog to output Verilog if you want to. It has deterministic synthesizable behavior. Thing which was also critically important for simplifying designs. We can apply Python object-oriented programming techniques, so we can pass in parameters to Python functions and classes which generate completely different HDL without having to duplicate that code, which is extremely complex. So it's a much better version of the parameterization of Verilog, which is not really neither Verilog nor VHDL are proper modern Turing complete languages. Well, you get the idea. So you can use Python-based for loops to read CSV files using a standard Python CSV module, which has been written for 20 years, and generate a hierarchical nested suite of HDL switch statements, and that's how we did the power instruction decoder for Libre-SOC. We also did some extreme abstraction for what's called a dynamic partition signal, which if any questions about that, I can answer about that later. So here you can see here's some VHDL in microwatt for the decode record, and here is the equivalent in nmigen, which the only evidence of there being any HDL at all in this is that signal, and that's an nmigen object, which represents a signal. So a signal of length 1, which is here, is a standard U logic, but a signal of length something is a standard U logic vector. But nmigen has the ability to support enums, and all of these are Python enums. And it will automatically detect the lengths and sort of thing. It's absolutely fantastic. So you're back to Python programming. You're doing software engineering techniques to develop hardware. And one important thing here is you can see that this subset argument, which is a Python set, if you pass in that subset, it will create a record which has a subset of the fields required, and consequently we can use this in the decoder to create subsets of the decoder for completely different purposes. So we use one decoder which we can use for getting the registers, all right? And this is all without having to write multiple versions of the same decoder, because it is the same decoder. You just pass in these parameters. And then use the same code to ask it to generate something for load store or something for the ALU pipeline, right? Simply by passing in a subset parameter of which limits the columns that are needed for that you want the code to generate. So in that way, we took this again from microwatt decode 1.vhdl. You can see this is the declaration of that ROM type. No, it's not. It's a op31 subtype array, but that array is of type decode ROM underscore T here. But in here, we've done it as a CSV file, and consequently, you can use the same CSV file to auto-generate documentation, tables, and many more purposes without having transcription errors and duplication errors in potential errors in the code. So again, there's no HDL in this at all, but it generates the HDL. Here's the decoder. So you have an array of things for dealing with the major opcode 19. Here's the other ones for 30, 31, 58, and 62. And then that is passed as sub-decoders to here, and that creates your top-level decoder of this major.csv, similar to microwatt decoder 1, the major thing, if you have a look at that offline. That contains the major opcodes, and it's based on bits 26 to 32 in power order, anything, etc. You get the idea. And then once that's decoded, and one of the switch statements is it goes into further into the hierarchy of further decoding, and ultimately you end up with one and only one of these lines being activated, and you've decoded the operand, decoded the instruction. So why we've done another vector instruction set? Well, it's not exactly another thing. It's called a tagging system. So there are no opcodes, new opcodes, and consequently, we stand a reasonable chance of fitting the simple V vector decoder into a single clock cycle, which you just can't do with the standard power instruction set. As I mentioned earlier, it's effectively a hardware subcounter for loop. You end up with a vectorization of not just the current instructions, but future scalar instructions as well. And so the element with polymorphism as part of the tagging allows, without adding floating point 16, 80, or 128, you get the ability to change the meaning of the scalar instructions for floating point 32 and 64 to actually mean 16, 80, or 128 without modifying the instruction set itself. So it's like an override system on top of what's the instructions. So this slide illustrates how that loop, that thing. Note that this is add, not vector add. This is a scalar add, which just happens to have simple V vectorization added to it. Looping round, here's the for loop. Here's where predication is applied to if it's enabled. And here you add on these increments depending on whether register A, register B, or the RT is detected in the tag table as vectorized. Hugely that's oversimplified, but it's basically that in a nutshell. So, apologise for rushing because it's actually time. I want to room for questions. Our goal is to create a mass volume, low power embedded system on chip suitable for netbooks, Chromebooks, tablets, and smartphones. It has to be trustable. This is our business objective. It is, despite the fact that it's Libre, the Libre licensed LGPLv3. That is part of the transparency of our business objectives, not because we just thought maybe it would be a good idea to be open. Collaboration with the Open Power Foundation and members is absolutely essential. There are no shortcuts here. We are fully keen on seeing and understand the implications of the Open Power end user license agreement. So we're working on the back of huge stability of the power ecosystem, and the combination of that means that our board support package can be 100% upstream right across the board, and this means that application and product development for our customers is greatly simplified and much more attractive. So thank you very much. Have questions?
Thank you. It was just we're on. I'll be on Freenode, IRC freenode.net on #LibreSOC, Libre-SOC. If anybody would like to chat, or we've also got the mailing lists. The website is libre-soc.org. So, if anyone has any questions, please do. Oh, see Q&A. Question there. What is the time frame for completion availability from Paul? Very good. We've got an end of October. Okay, so it's working now with microwatt compatibility is functional. So that's in FPGA. The test chip will be the end of October, going to the foundry. So that's 180 nanometer, but that's a test chip. So we need special permission from the Open Power Foundation to do that, but it's not going to be publicly available. Then realistically, we're looking at about 18 months for something like a 28 or nanometer or below ASIC. Hope that answers. Any other questions and thoughts? So, as one thing, this is a Libre project, we actually do have funding from NLnet. So, if anybody wants to help, they're more than welcome to do so, and actually receive donations for doing so. That's. We've also got we're doing 2 drivers, 2 3D drivers, and some video drivers. The video drivers being done in assembler for inclusion in FFmpeg. And there's 2 3D drivers. One of them is in Rust, both of them are Vulkan compliant, and the other one is MESA driver. And that's that MESA one is actually going to be a sort of a software one, which then ends up being hardware accelerated. So it's a huge scope in this project. Absolutely fantastic. I'm just absolutely amazed that it can consider it even be possible, and it wouldn't be possible without the huge ecosystem that's available in open source software. If any other questions, yeah, feel free to get in touch on the IRC channel or join our mailing lists on lists.libresoc.org.